Hello everyone, my name is Jonathan Harris, and today we are continuing our Build Your Own Botball Library series, and we are going to be looking at how to make a square up for your library. And I talk about square ups a lot in all of my Botball analyses. That's basically all I preach, is to square up, square up, square up. It's the key to making an accurate and precise run, because if you've seen the drive functions and the turn functions of the library we've made so far, you know these do not get you a precise straight drive. They do have some variance and tolerance depending on the motors that you use, the battery level that you use, and so you need things that are going to get you localized on the board. And one of the main ways to do that is with square ups. And today I'm going to teach you how to use a black line follow sensor square up. So a black line follow sensor square up is different than the other type of square up, which is a PVC pipe square up. A PVC pipe square up is where you just take the flat part of your robot and you back up into the pipe. That's the main way of squaring up. That's the way I would usually suggest a square up, but sometimes you need to square up without a piece of pipe there and there's only a black line. To do this, all you need is two line follow sensors. Usually I would suggest, for the square up sensors, here's what I usually suggest: is for squaring up, we use the small top hats. And for the line following, we use the large top hats. And we talked about line following a while back in one of our tutorials. So today we're going to be looking up at square ups using two of these sensors to align ourselves not only in one axis, but also rotationally along a black line. Here's the setup I'm using for this test. It's just a demo bot, but then we also have just some 7x1 slapped on there. This is just what I had laying around the house. And then black pegs are on those, and we're giving them a little bit of lift off of the table, but on an actual bot, you might want to lift them up a little bit more. Usually it's good to have about a spiked nut worth of distance between the square up sensor and the table, but for what we're trying to do, this will work perfectly fine. So here I have our coding window, and like usual, we're just going to start by writing the function in the main, and then after that we can go ahead and put it into a function that you can paste into your library. So what is a square up? A square up is pairing two sensors to the wheels. So the right sensor goes with the right wheel and the left sensor goes with the left wheel. Then each of those wheels is controlled by that sensor to line it up on the tape. That is the behavior that we are trying to replicate. So this is something that we want to repeat until we reach a certain criteria. We want the robot to continue to drive forward either from one wheel or the other or both until both of these two sensors are reading black. So that means we're going to write a while loop. And inside this while loop, we're going to write, and let's go ahead and do some good practices here. Let's say we're going to define right, and this is how we define a constant, right? We're going to define a constant, and right is always going to be equal to 0, and then we are going to say that left is always equal to 1. So we can say in here, remember we know how to pull data from an analog sensor, while analog of the right wheel, and this is basically the same thing as putting a variable, but instead it's a constant. It's never going to change. That define is always going to be 0. So when I type in right, it's always going to be 0. So while right is less than some gray value that we are going to find in a second, or this is how we write an or in C. The or is basically saying while one or the other sensor is on white, we want to continue. The only time we want to exit this loop is when both are on the black. So while either one of them is on the white, we continue running this loop over and over again. So while analog right is less than gray value, or analog left is less than gray value, and we're just going to go define gray value up here. If you're writing your own library from all of these videos, chances are you already have your own gray value defined somewhere else. And maybe you can make gray value a variable above all of your functions so that you can have the same gray value for your square ups and your line follows. But I'm just going to go ahead and say gray value, and the way to find your gray value is by looking at your robot, and you're going to look and you're going to go into the sensor graph or the sensor list, and you're going to put your robot on the whiteboard. So I have my robot on my testing table right here beside me. Right now, when I'm on the white, I am getting a value reading of 200, roughly 200. It's closer to 210. But then once I push the robot onto the black, I get 3,700. So what we're going to do is we're going to take the average of those. So we could go ahead and write that into our gray value so you can kind of see what's happening. So our gray value is going to be 200 plus 3,700, and we're going to divide that by 2 because that's how you find the average. You add them all up and then divide by how many numbers you added by. So there's our gray value that is directly in between the white and the black value. That is what we're going to use to detect whether or not something's on the white or the black. So inside this code, here's what we're going to write. A couple of if statements, right? Because we're trying to make the wheels act in a certain way depending on different scenarios. So that is an if statement. So I'm going to say if analog right is less than gray, then this means we are on the white, right? Now, else means, I should be more specific here. The right sensor is on white. Then inside of here, I can say right sensor black, right? This is what we're going to be using to control the right wheel, because this will be true inside of here if analog is less than gray value, meaning it's on the white. And else means that if this is not true and it's false, then the second parameters will be run. It might not be immediate why we need the second set of parameters, but it'll make more sense in a minute. So all we have to do is say the same thing for the other wheel. If analog left is less than gray value, then we know left sensor is on white. We'll finish up our else statement here. Left sensor is on black. Something to note here, I have defined right as 0 and left as 0. What that's meaning is I have plugged my right motor into port 0 and my left motor into port 1. I have plugged my right analog sensor into port 0 and my left analog sensor into port 1. That's just an easier way to get it to where in your head, this is what, it makes it easier to look at in the code. And this is just something that you're going to have to plug in and keep track of when you are actually setting the ports on your robot and how you plug in your motors and sensors. So now we actually need the robot to move. If you'll remember, I prefer to use MAV. I like the 0 to 1500 range. It's my personal preference. But if we're on the white, that means we have not reached the black line yet, and we need it to move forward. So we're going to say the right motor needs to move forward, and for now, we're going to say 500. Right? Same thing for the left wheel. 500. Now, you might be thinking that this code already works. What else do I need? When I see white, the wheels move forward. When I see black, the wheels don't do anything. But that's not actually quite how this works. Remember, wheels act on the last command given to them. If the last command was this and we don't give them another command in here, they're going to continue to do their old command. because the loop is still running. So we can't assume that the wheel is going to stop. The only thing that will make this stop is return 0, but that's not going to happen most of the time. So this is actually not a correct square up. What we need to add in here is what we want it to do when it sees black. When it sees black, we want the motor to stop. So to make that motor stop, all we have to do is say speed 0. That is going to lock the motors in once they see black. When you run this code, it's going to work. But you might notice something when you start playing around with it. Number one, there's two problems with it actually. Number one, it doesn't line it up properly. The whole point of a square up is that it lines it up properly, but it's not lining it up properly on the line. It always has a little bit of variation to the left or the right, unless when you set up the robot, you point it directly perpendicular to the line. But if you add a little bit of an edge when you stop it, it's going to have a little bit of a tilt in it. Another thing is it slowly drifts to a stop, and also adding another layer of inconsistency. So what we actually need to do here is add in a lock like this. We've done this before, but we are basically giving it the last commands it needs to do. If we tell the motor, if we kill the program, the motor is just going to drift to a stop. But if we tell it to lock itself at speed 0, then it's not going to free spin after the function is already over. So if you run that, we're going to eliminate one of the two problems. But the other problem persists. When we tell it to square up, it always has a little bit of an angle one way or the other. The reason for that is these line follow sensors are not perfectly lined up with the wheels. We are telling the motor to stop, and we are pivoting from a point that is not the center of the wheel. And so if the left wheel stops and the right one continues, well, that other sensor that has been told to stop moving is still rotating because it's not directly at the origin of the pivot. There's a very simple way to stop this. We don't actually tell the motor to stop. We tell the motor to go slightly backwards. And actually, I'm going to go ahead and give it 20. We'll try that, and we're going to fine-tune this. We tell it to drive backwards so that although our point of rotation would be back here, we're actually adjusting it to where it goes over the white line again. And this might make sense when I show a video of what it actually looks like when we compile and run this code. So I just ran the code. We are still seeing a little bit of variation in that. So I'm actually going to crank this back to be like 50. And we're going to see, what you want to see is the most, when you're doing this type of square up, you want to see the straightest line possible with the least amount of jiggle. Because when you do too much, it's going to hit that line and it's going to go back and forth, back and forth, back and forth, back and forth. That can happen. And I'll show you a video of what that looks like here. So this is not enough. This is too much. And you're going to need to fine-tune this for exactly what your robot needs, and it's going to change depending on where your sensors are to your wheels. And it looks like for this speed and how I have the sensor set up, -200 is what is working properly on that square up. So I've just been playing around with some more values, and anywhere between the 300 and the 200 range seems to be working fine for speed 500. But let's go ahead and write this into a function so we can see what is going to happen when we have an actual speed parameter that they can set inside of the square up function. I'm just going to define it up here, but remember you can put it into your library later on however you want to set that up. Now that we have that, we're going to go ahead and bring all of this code into the function like that. And we actually, like I said, we're going to leave the gray value out here, and we can go ahead and make it a define up here. All right, we've defined our gray value right there, and now we almost have the entirety of our square up function, but we want to, instead of using these hard speed values, we want to be able to let the user input a speed value. So I'm going to say speed is one of our parameters, and the moving forward is going to be speed, and the backwards, just as a hunch, if we use 500 forward and we are using negative 300 back, what if we use negative 3/5 of our speed? Would that work? Let's try it out. I have no idea if this is going to work. If it does, that'd be pretty cool. Let's try it out. It might work. Now we already know speed 500 does work, so let's try the extremes. So we're going to try speed 100, and we're going to see if that does what it's supposed to do. So I've been doing some testing. That doesn't seem to work. Let's go ahead and, just so it's a little bit easier to play around with, let's make this something like 0.8. Basically, it's just any value less than what our actual speed value is. Because it's kind of like 2 steps forward, 1 step back type thing. It's going to at least be progressing us. It seems to work at that. Let's go ahead and do another test point. And I'm trying at very extreme angles here just to make sure that it works no matter what you're doing. Okay, so that adds a little bit of jitter. I don't think it's an issue. I think if we can get this working at the extremes here, I'll be pretty happy with it. That seems to work. I would say, whatever you're doing, play around with this value. That seems to be working rather well. And I'm getting... Let's just go extreme here. Yeah, that does it. Okay, so that is the entirety of the square up function. So just to reiterate what we're doing here, remember we want that rotation since they are not perfectly lined up with the wheels. Unless they are. If they are perfectly lined up with the wheels, then you can set this to be 0. And this is something you're going to want to play around with depending on where your wheels are set up, is how much it needs to crank back by. But that is the square up function. It's really simple. It is so useful to use in your code. I think squaring up on the pipe is definitely my go-to, but if you have the sensors available to put these on your robot, 100% would recommend doing it. And I have a lot of analyses over doing just this type of thing, especially my first analysis video that I did. It was very much based on smart positioning and squaring up properly. So I think this is going to help you guys very much with whatever you are intending to do in your Botball run. And like I said, I want to try to give you a little bit of a challenge. I don't want to give you all of the code. I want to give you 80% of it, and then you can, and it's working code, it's good code, but I want you to try to take it a step farther yourself. And so for this, I want to I just want to lay a thought in your head that when we used a line follow, and we used a smooth line follow, we used a proportional value because we looked at how white and black is not binary. It's not white and then hits black. There's a whole gradient from white to gray, and how we don't turn back as hard if we're only halfway on the white. And so there is some room for play to smooth things out there. How could you add that to this to make the square up more smooth? How could you make it to where the speed that the wheels are moving is proportional to how much white or black that those are seeing on the sensor? that's what I leave you with today. I hope this was helpful. If it was confusing in any way, please let me know. I'm almost always available on the Discord. I try to help as many people as I can. I think after this one, I'm going to do a couple more analysis videos, and then I think I might start trying to look at some more advanced tutorials for teams who want to take it a step further and kind of look at the math on those. Maybe not tell you about the code as much, but at least look at the theoretical math behind everything. So, thank you. I hope this was useful. Have a good day.